Hypothalamus Artificial Intelligence, HI. It presents companies in the process of digital transformation, its offer of professional services and the supply of algorithms of highly complex multi-problem mathematical models. These services are optimization applications in the forestry sector. To provide these services, HI is supported by its business partners, GAMS, IBM and TD SYNNEX, all of which are producers of artificial intelligence technologies. HI is a company at the forefront of high-performance artificial intelligence. Operations research applications in the Chilean forestry sector. A case of business cooperation. This presentation is based on the article Use of Operations Research Systems in the Chilean Forest Industries. In 1999, the Chilean forestry sector generated about 13% of exports, which include logs, wood pulp and sawn timber. It was the second economic sector, after mining. The sector grew by 12% during the last 7 years of the last decade of the last century and has good potential for further expansion in the next 20 years. The forestry sector was one of the growth engines of the Chilean economy from 1985 to 2000. The Chilean forestry sector is made up of private companies that combine large areas of wood, mainly pine plantations and some eucalyptus, with sawmills and pulp mills. To compete in the world market, since 1988 the main Chilean forestry companies, which have annual sales of around $1,000 million, began to implement operations research models developed jointly with the University of Chile. These systems support decisions about daily truck scheduling, short-term harvesting, location of harvesting machinery and access roads, and medium and long-term forest planning. Approaches used to solve these complex problems include simulation, linear programming with column generation, mixed integer formulations, and heuristic methods. Mathematical models have led to a shift in institutional decision-making and estimated profits of at least $20 million per year. Chilean forestry companies have always had a high level of cooperation. In 1988 they organized themselves into an association called Grupo de Producción Forestal, GPF, coordinated by Fundación Chile, a non-profit institution formed by the Chilean state and ITT, to promote the development of Chile. Thanks to this initiative, the management of Chilean forestry companies changed and facilitated the introduction of optimization systems at the different levels of decision-making. Since the implementation of the technology in 1989, the top 5 firms report minimum annual savings of $20 million USD, 25% savings in operational costs. The main companies are Forestal Arauco, Forestal Mininco, Bosques Arauco, Forestal Valdivia, and Forestal Bio. The relationship between the participants facilitated the joint development of the mathematical models, which means that the software has become jointly owned, demonstrating the willingness of companies in this sector to cooperate by sharing technical developments. Decisions that are supported by mathematical programming models include strategic, long-term decisions of harvests and plantations with the aim of maximizing sustained and sustainable agro-industrial production, preserving the environment. Tactical decisions, in the medium term, which are mainly concerned with the sequence of areas to be harvested and the roads to be built to meet estimated demands. Operational decisions, related to the way of using and harvesting crops. The mathematical models implemented by the Chilean sector are operative, AGCAM, a truck scheduling system. OptiCort, a short-term harvesting system. Tactical, PlanX, a machine location and road design system. OptiMed, a tactical forest planning tool for planning 2 to 5 years. Strategic, MEDFOR, a strategic tool for forest planning with a planning horizon of 50 years. The table shows the estimates of the costs avoided by the mathematical models for the year 1997. AGCAM, a truck scheduling system. A major problem in forestry operations is deciding how to transport timber from different origins to destinations, such as pulp mills, sawmills, sorting yards, and ports. The basic objective is to satisfy the demand for the different products to each customer, minimizing transportation costs. In 1999, 10 to 90 origins, 5 to 30 destinations, and 50 to 300 possible routes were handled. 8 Chilean firms had implemented AsiaCam, reporting cost savings of between 15 and 35%. These results, certified by the beneficiaries, should not go unnoticed. The average savings of 34.1% in installed capacity, equivalent to 48.8% of over-installation, are factors that affect competitiveness. The excess of trucks does not lead to higher production, but it does lead to higher investment and operating costs, which must be borne by companies and, therefore, by society. The difference in productivity is systematic and can only be explained by the value added by mathematical models. The number of trucks that the 4 forestry companies needed to transport similar volumes of wood decreased with the implementation of AsiaCam. This implies excess installed capacity, and the difference indicates the number of trucks that have been purchased in excess, i.e., trucks that do not generate profits and are presumably generating unnecessary expenses. Bad decision-making practices are money thrown away. There are many ways to program routes, but only a few guarantee to harness knowledge to achieve minimal costs, a highly mathematical problem. This is independent of the vehicles used and the products transported. It is not a question of suitability, nor of will, but of access to knowledge to find the best decisions. When comparing the number of trucks before and after AsiaCam, the over-installation of capacity in trucks is evident. OptiCort, a short-term harvesting system. Determine the diameter and length of each of the parts. Since 1991, 4 Chilean firms have been using OptiCort. This representation shows the separation patterns. The bottom of the tree, below the defect, leads to an export piece, with some residual wood as pulp. The 6-meter section above the defect can be used as sawn timber. Next, the use of 2 different parting patterns is analyzed. Pattern 1, obtain a piece 12.10 meters long and 24 centimeters in diameter. Then, a piece of 4.10 meters and 20 centimeters is found, and the rest of the tree becomes pulp. Pattern 2, obtains 3 pieces, one 8.10 meters long and 24 centimeters in diameter. It can reach 29 centimeters. Then, you get 2 pieces of 4.10 meters and 20 centimeters, and the rest of the tree becomes pulp. The diameters shown in each schematic figure are actual values. The best part depends on market prices and commitments made through bilateral contracts. OptiCort also produces savings in transportation. For example, Bosques Arauco saved $250,000 annually American dollars when the model indicated that was better to transport directly to the destination, about 50% of the volume being transported through intermediate sorting centers. The image features a simplified algebraic formulation of OptiCort. Typically, OptiCort runs every 2 weeks, on a rolling horizon of 3 months. In 1999, OptiCort was running on commercial LP code on a PC in about 10 minutes. PlanX, a machine location and road design system. It plans the machinery and the optimal location, as well as the design of short paths to carry out short-term operations. Since 1996, PlanX has been used by 4 Chilean firms. Its use makes the work of planners more efficient than the manual systems used previously. In the first years of use, Forestry Bio estimated savings between 0.5 and 1.5 American dollars per cubic meter, with an annual production of 400,000 cubic meter. Forestry Bio reports reductions in the road network of 50%, which means annual profits of at least $2 million of American dollars. The main objectives of mathematical modeling are: locate harvesting machinery and design the road network at the lowest cost. Reduce the environmental impact on the felled land. Minimize the costs of operating, building the road, and moving the wood to the storage centers. Cell characterization should be considered. Physical and economic characterization based on parameters such as planted volume, age and height of the trees, vertical slope, horizontal slope, longitude, latitude and height of the cell, type of soil, and all necessary parameters according to the model that is implemented. Each cell behaves as a node, and the arcs are the connection to other cells and the collection point. Since Chilean forests are mostly found in mountainous areas, the design of harvesting systems is complex and must consider a variety of technical constraints. Restrictions such as topographic variation of the terrain, availability of wood, types of machinery, environmental impact management, and projected budget. Tower anchors should be located according to topographical conditions, and each tower should be located according to its range of reach, depending on the type of tower, operating conditions, and terrain characteristics. The restrictions to be considered are area restrictions for disembarkation and connection, 10 mts high each tower, conditions of accessibility to the road networks, and connectivity conditions from the harvest areas to the towers. In the transport of wood to towers, the company must granitize certain connectivity conditions. For example, making sure that the reach of the cable is not interrupted by a river, and consider the availability of equipment and the operation of connecting cables from a specific location to a tower. Roads should also be built with adequate characteristics, including an acceptable slope and a minimum turning radius for trucks. Conditions to consider: prevent tractors from turning, minimum radius, ground conditions, and slope conditions. To ensure that the topographical conditions allow the skidder's operations, basically determined by the slope of the terrain, limitations such as ground conditions, inclination, excavation cost. In this example, the light shaded area shows the area harvested with skidders, while the dark shaded area represents the tower harvest. The full lines show the connecting road network, while the black dots indicate the position of the towers. The results in productivity can be summarized as reduction of road construction by 60%, and savings of $1 million annually. In 1999, this methodology was applied in 9 Chilean forestry companies. The model is a mixed linear programming problem of network planning with 100,000 cells and 800,000 arches. Plan X is fed with cartographic information and with the technical and economic parameters determined by the designer. OptiMed, a tactical forest planning tool. Mathematical model of medium-term tactical planning, 2 to 5 years. It is a medium-term tactical planning tool, 2 to 5 years. It determines the public and private roads of access to the crops, considering the type of product demanded, and the seasonality of the climate. Forestal Millennium has been using OptiMed since 1994. Profits in this case are more difficult to estimate due to the length of the planning horizon. OptiMed is based on a binary programming model that determines the construction and updating of tracks, from track gauge to gravel, taking into account the fixed and variable cost that this implies. The solution poses difficulties due to the number of variables of road construction and adaptation. To overcome this disadvantage, a combination of mathematical schemes was used, including strengthening the linear formulation and heuristic rounding of variables. In 1999, the model ran on a PC with commercial LP code and typically took about 30 minutes to run. Lagrangian relaxation was useful in some cases, but it was not implemented for companies. MEDFOR, a strategic tool for forest planning. Mathematical model of strategic planning with a planning horizon of 50 years. The main features of MEDFOR are: strategic planning tool with a 50-year planning horizon. They determine crop rotation, planting density, and geographic location. Establish negotiation policies. MEDFOR was designed to support long-term, sustainable wood production decisions that consistently meet the demand of industrial plants and exports. In addition, it serves to select plantation forest regimes, establish long-term contracts and determine the purchase and lease of land. Mathematical modeling to reduce wildfire spread. Although Chilean models do not consider the serious risk that forests must face for 50 years, modern methodologies include this topic. Such is the case of forest fire management. Wildfires are an important ecological process in forested regions around the world, which can cause significant economic damage and often lead to widespread health impacts and environmental pollution. A network optimization approach to plan combustible material treatments in wildfires that minimize the risk of fire spread, in forest landscapes below an upper limit for the total treated area. Simulation models are used to estimate the probability of fire spread between pairs of forest sites, and a critical node detection (CND) model is formulated that uses these estimated probabilities to find a pattern of reduction treatments with combustible material that minimizes the probability of fire spread. Mathematical modeling controls the size and spatial contiguity of combustible material treatments. The article, Detecting Critical Nodes in Forest Landscape Networks to Reduce Wildfire Spread. It studies how best to locate fire barriers during the forest design process and, subsequently, how they function when a catastrophic event occurs. Case Study: Kootenay National Park, British Columbia, Canada. Another case reported in the technical literature is an integer linear programming to select model and temporally allocate resources for fighting forest fires. The paper presents mathematical modeling with a case study in Kootenay National Park, where the authors investigated prescribed burning options to reduce the risk of wildfire spread. The results provide new insights into cost-effective planning to mitigate wildfire risk. This approach is applicable to ecosystems for the design and redesign of industrial and/or environmental forests. Nowadays it is possible to plan the location of fire barriers in such a way as to minimize the damage that fires can cause to plantations and living beings. Optimal planning of the amount and type of resources, human and industrial assets, needed to extinguish a wildfire is a difficult task. However, the coordination of resources, as well as the economic, social and environmental costs involved in fires, make the planning and operation of fire mitigation activities critical. This study proposes a general model of complete linear programming, which addresses the allocation of resources in different periods during the planning horizon defined for the extinction of a fire, with the aim of complying with current regulations, including the non-neglect of fronts and rest periods for human resources. Experience with the model shows that an exact solution can be obtained without the need for heuristic algorithms. Resources scheduling to fight a forest fire. The authors report a test case of a single fire, for which the model selected 10 resources to work on fire containment. Helicopter 1 and Team 12 Brigade 3 continue to work to contain the fire. Helicopter 1 is currently on a rest period. On the other hand, Aircraft 2, which does not appear in the figure, finishes its work to contain the fire, because it is already more favorable to incorporate a new resource. With the optimal solution proposed, it is possible to contain the fire in period 11, with a total cost of €25,440. The model can be extended to consider multiple fires simultaneously. Everything indicates that good harvest planning will be critical to ensure that harvesting is profitable while environmental quality is maintained. Alfred North Whitehead affirmed, "Algebra is the intellectual instrument which has been created for rendering clear the quantitative aspects of the world." Thank you for your attention.